Good morning. So today we are going to continue with the part 2 of optical fiber, that is types and numericals. So in the last topics we have discussed that an optical fiber consists of a wire which has got some central part as core, outer part as cladding, and the center part is thicker and outer part is thinner because it works based upon the total internal reflection. So TIR, which says when the light moves from denser to rarer, if it strikes at an angle greater than the critical angle, it undergo total internal reflection. So that phenomena we have signed out, and then we have find out the relation sin C is equal to N2 by N1. Then we have discussed how the optical fiber made up of. We have seen there were three kind of fibers: all glass, then plastic coated silicates, and then all plastics. And their configuration was discussed. What are the materials it is made up of, and all these things were being discussed. And today we are going to and then we have discussed a formula how the light is propagating into the fiber, that is theta A is equal to sine inverse under root of n1 square minus n2 square upon n naught, where n1 and n2 are the refractive index of core and cladding, and n0 is the refractive index of the medium. So for generally we take the medium to be air. For air, refractive index is equal to 1. So the angle of acceptance comes out to be equal to sine inverse under root of n1 square minus n2 square upon n0. So this is upon 1. So this is 1. So that means the acceptance angle means the angle at which the light is accepted into the fiber. So then the maximum light which is going to be accepted in. Now then we define another parameter which is called as an acceptance cone. Acceptance cone means, let us say this is the angle at which the light is accepted. So the light can accepted into the other way also, like to this way. So that means this light is going to make a certain kind of cone which is called as an acceptance cone. So acceptance cone means the maximum point of the light which is going to be get added from the either side of the fiber, so that the light can propagate inside the fiber in two ways. So that is called as an acceptance cone. And then we have to decide, we have taken two material, one was core, another was cladding. So how much should be the refractive index? The difference should be in the refractive index of the core and cladding. So there is an important parameter that is called as delta, which is called as fractional change in refractive index. Fractional change in refractive index, which is defined as ratio of n1 minus n2 upon n1. So that means this value should be always greater than 0, because for optical fiber to exist, n1 is always greater than n2. So that means delta is always greater than 0. So it can never be 0. But delta should be a small value. For a proper optical fiber to be this one, optical should be greater than 0 but should be much lesser than 1. Smaller the fiber delta and greater will be the optical fiber, because at smaller angle the light will be get accepted into the fiber. So, and the sine of theta, so that is called as an numerical aperture, that is the light gathering ability of the fiber. So numerical aperture, basically we know, let us say a triangle is being taken. This is theta, this is perpendicular, this is hypotenuse. So sine theta is taken as perpendicular upon hypotenuse. So this optical fiber, that is numerical aperture, is equal to under root of n1 square minus n2 square, which we have derived it out earlier. We can derive it in another way also. In another way, how we can do it? Let us say this is a practical aspect of it. We take a fiber and then allow the light to propagate through this fiber. This is the axis of the fiber. Let us say the light is coming out from this one, and then from the other end the light is coming out to be hit. Let us say this is the screen where the this picture is being formed. Let W is the diameter and L is the distance from the screen, and let us say this is the theta. So this theta is going to be taken. Now let me say we draw this one. This is a perpendicular. Let us say when we perpendicular draw it out, so this will be W by 2. Now call this as triangle A, B and C. So in right angle triangle, now let me calculate the value of AB. AB is the hypotenuse, which is equal to L whole square plus W by 2 whole square. So that is the value which we are going to take it out. So that is equal to under root of L square plus W square by 4, or we can take it as 4 L square plus W square upon under root 4 is 2. So this is the value of A. And sine theta we can take it as perpendicular upon hypotenuse. Perpendicular is about BC upon AB. So that means BC is W by 2 divided by under root of 4 L square plus W square upon 2. So this 2 to get cancelled. So that means sine theta, which is equal to the numerical aperture, can be written as in this form, that is equal to W upon under root of 4 L square plus W square. So that means practically we can calculate the numerical aperture by this relation. So this relation will be very rarely available because only in the laboratory we are going to use it out. Theoretically, in theory we used to do the formula of under root of n1 square minus n2 square. So then now we are going to correlate how numerical aperture is correlated with the delta and fractional change in the refractive index. So we know that numerical aperture is equal to under root of n1 square minus n2 square. So that is equal to under root of n1 minus n2 into n1 plus n2, because we have applied the formula of a square minus b square into a square plus b square. So a square minus b square is equal to a minus b into a plus b. So this identity we have applied over here. So we can write this as delta n1. Delta is equal to, we know that delta is equal to, we have written delta is equal to n1 minus n2 upon n1. So which means n1 minus n2 can be written as delta is equal to delta into n1. So that will be taken into out. So that means numerical aperture can be written as under root of n1 into delta into n1 plus n2. Now let me do it one thing, that n1 plus, since n1 and n2 are very small, so we can take this n1 plus n2 is equal to approximately twice n1. So we can take it as twice n1 square into delta. So that means it is equal to n1 under root of twice delta. So that means numerical aperture can be calculated by this relation also, that is equal to n1 under root of twice of delta. So that is another relation which we have to calculate it out. Now the problem arises. Let me discuss one problem and then the technique to solve this problem. Problem is that a fiber is given with core of refractive index 1.5, and cladding is doped to give fractional change refractive index is given 0.0005, and then we have to find out number 1 refractive index of cladding, number 2 critical angle, number 3 acceptance angle, and number 4 numerical aperture. So what is the technique to do this calculation? So first of all, we are given refractive index of core. How we will represent it? It is represented by n1. So now we know that delta is equal to n1 minus n2 upon n1. So put the value of this one 0.005, that is equal to n1 is about 1.5 minus n2 upon 1.5. So when you solve it out, most of the answers come out to be 1.49925, and most of the students, they used to take it as approximately equal to 1.5. So when they get to take it this one, this will be wrong because n1 and n2 will be same, so the fiber will not exist and no propagation of light will take place. Some will take this value as 1.49, so that means the fractional change value has not been considered and this value has been enlarged. Again, the angle of acceptance will be wrong. So whatever the value of this is given, so you have to take the fractional change. According to that parameter, you have to do the calculations. So that is the first part, which is very, very important. Then when you are doing the another part, sin C, that is n2 by n1. So put this value 1.49925 divided by 1.5. So then this will be the value of sin C, so that you can get it out. But we have to find the value of C, that is sine inverse of it. So sine inverse should be taken properly in the calculators, where some operation should be taken care of. Inverse operator should be done, and then we are going to do the calculation, and that value should be approximately 88.12 degree or 88.2 degree. So if your angle coming out to be 87.78 degree or 87.8 degree, it means Your critical angle is this one. Critical angle means the angle at which the light will be cut off is up to this one, but actually the light is cut off at this angle. So that means this calculation will make your numerical to be wrong. So that's why the calculation part and the numerical part are very, very sensitive in this chapter. So that you have to taken care of. And then we have to find out the next part, that is the acceptance angle. Acceptance angle can be find out, that is equal to under root of n1 square minus n2 square. Now what to do the values? 1.5 whole square minus 1.49925 whole square. So that you have to do it out. So again the proper value of squares has to be taken care of, and then you will find out approximately value to be approximately equal to that will be equal to 2.72 degree, 2.72 degree. And then this value should be again matchable, because this is the angle at which the light is accepted into the fiber. And then the next part is about the numerical aperture, that is about the formula. You can use it anyone, either you can use sine theta or you can use n1 and root of twice delta. So any one of the formula you can use it out, or so you can find the value to be 0.0474. So this is the value at which the numerical aperture, that is the light gathering ability of the fiber, is this one. So this was a particular important question. Now next question is very, very important. So that will be the most important part, because these kind of questions used to come out in the examination and you have to solve this properly. So at the end I will give you some problem to do this and solve it out properly. Now an optical fiber has numerical aperture of 0.20. Next question is question number 2. Numerical aperture of 0.20, and then we are given a cladding of refractive index. Cladding refractive index is 1.59. Now find the acceptance angle in water. That is the main problem. Water has a refractive index of 1.33. Now we are given an optical fiber which is placed in the air. In air the numerical aperture is given to you. So that is numerical aperture is 0.20. What is numerical aperture? That is equal to under root of n1 square minus n2 square, and that will be this one. Now for n0, because air is 1, so this will be taken, so this value is given to you. Now for water, when the fiber is placed in water, means water is being taken and fiber is placed here. Now what happens? The medium around the fiber will be the water, so in that case the n0 will be changed to 1.33, and numerical aperture for that will be equal to under root of n1 square minus n2 square upon n0. So n1 square minus n2 square value is already given, that is 0.20 and then 1.33. So this value is being taken, so that values comes out to be approximately equal to 0.15. And since we have to calculate the acceptance angle, so sine inverse 0.15, that is equal to 8.6 degree. So that is the value which you are going to take it out. So this is the most important question which many times used to come out to be in the paper, because you cannot able to apply, where to apply which formula and why to take this value of n0 over here, because according to the question the water has been placed in the fiber water, so that's why this calculation has to be taken care of. So these topics we have discussed about the numericals, the formula, the application, acceptance con, numerical aperture, and then about how the different fibers, the techniques to solve these problems, and then how experimentally the numerical apertures can be calculated. So all this will be discussed. So in the next lecture we will calculate the type of the optical fiber. Thank you.